I wanted to do an overview of the math that I left for you to do today. Apologize for being gone. I suspect you guys are probably missing me pretty much. But here we go. So we have a graph. It looks like this. Remember the graph we made at the first day back from spring break? We melted ice, and the ice flatlined. Then after it melted, it warmed up, and then it started to boil and boiled for a long time. We never did get it to all boil away. But if we had kept boiling, it would have gone up like that. And then if we had measured the temperature of the ice as it came out of the freezer, it'd be right here. We'd be down below zero. So you remember this temperature is 0, and this temperature up here is 100. This is freezing or melting, and this is boiling. We had three equations that I gave you. The first one that I'm going to write down is this one. That's the equation you use anytime there's a change in temperature. So that applies here. It applies here, and it applies here. Anywhere there is a change in temperature. Remember, on this axis we have temperature, and on this axis we have time. Here where the water was melting, it was Q is equal to mHF, and where water is boiling, the quantity of heat was equal to mass times heat of vaporization. So 3 equations: boiling, melting, or freezing, because if you're going that way it's freezing, if you're going right to left. And then this equation is anytime there's a temperature change, you use it. So just as a quick example, suppose you had 10 grams of water at 25 degrees C, and you wanted to go up to, say, 110 degrees C. First thing you do is find 25, which is about right there. Somewhere in there, whoops. Right there. About 25, because 0's here and 100's up here, 50's there, so 25 is about 1/4 of the way. 110 to be somewhere up in here. Put my 25 back, I took it away. All right, so really we've got to go up, and then over, and then up again. So when you're going up, the quantity of heat involves a temperature change, so you'd use the Q is equal to mCp delta T. This is not always the first temperature that you use, but if there's a temperature change, that's the first one you use. Now, once again, I'm talking about right here. We're going to add to that whatever the heat of vaporization times the mass is. So we're going to use that formula. That looks like a G, it's supposed to be a Q. There we go, fixed. And then we're going to add the quantity of heat using this formula. Now, really, I wrote this because I wanted to just recreate what I have up here, but really it becomes mCp delta T plus mHV plus mCp delta T. Remember, here you got to use liquid water, that's liquid, and here you got to use steam. And there's different values for the specific heat capacity of water and steam, and that's listed on the handout. So then so bottom line is you just identify the energy changes, or excuse me, the temperature changes that you're going to do, calculate their energy and add them together. So you just got to manipulate yourself. You have to navigate around the graph a little bit. And so if, like, for example, if you started down here, you'd have 1 and you want to go up to 25. If you started here and you wanted to go to 25, you'd go up, over, up. 3 steps. If you started here and wanted to go to 25, it'd just be over, up. If you start at 0, just 2 steps, and you add them together. Now you can look at the examples in the handout. They do a nice job of going through 2 problems as examples. And then there are 5 problems for you to try. And we'll talk about them on Wednesday, I'm sure. So do your best, and see you on Wednesday.